The theory behind this lab is all about diffraction, and our good friend Huygens tells us that when we have a wave and it's incident upon an aperture, we can treat each position on the aperture like an infinite number of tiny wavelets. And we start getting diffraction due to this OPD difference. So if we look at a wavelet that's off axis and we compare it to the wavelet that's on axis, we have this different optical path length, and that's going to give us an OPD from the on-axis case. We can figure out the phase relative to the on-axis case from this formula here, where the OPD is dependent on the off-axis travel length in comparison to the on-axis travel length, as denoted by this equation right here. When we have diffraction off of an aperture, it creates these different Fresnel zones, which can be outlined here, where this is the extent of our aperture and it's rotationally symmetric. A represents the radius of our aperture, and you can see the different alternating bright and dark Fresnel zones here. Each one is separated by a half wavelength OPD difference between the boundaries of each zone. We can represent the total number of Fresnel zones within our diffraction pattern based on the size of our aperture, the wavelength being used, and L, which is a function of source position and observation plane. Because Fresnel zones are separated by a half wavelength OPD, we know that each subsequent Fresnel zone will destructively interfere with the first one. For example, when we have two Fresnel zones present, the second interferes with the first one, causing destructive interference and a dark spot at the center. But if we were to add another Fresnel zone, making it 3, the second would still interfere with the first one, but we would still be left with the third one, causing a peak in our irradiance. So for every even number of Fresnel zones, we'll have destructive interference with a dark spot in the center, and for every odd, we'll have a bright spot in the center. This can be shown by this curve where each odd corresponds to a peak in the irradiance, and each even number of Fresnel zones corresponds to a minimum.
We built a Keplerian beam expander to expand the beam. We used a 20x numerical aperture objective and a 10 micron pinhole. As the light comes over here into a little aperture, we measure the size of the aperture. We had a microscope aligned with the crosshairs. Knowing the size of the aperture, we calculated the Z2 to be about 35 centimeters. We went further out. As you can see, it's a bright spot. As we move in, the bright spot become dark. That's the first Fresnel zone, and when it's completely dark, when NF equals 2. As we change the aperture size, we can see that the Fresnel zones change.
It's because it's a...
For this part of the lab, we wanted to use the Fresnel zones to help determine the best focus of a test lens. And so the way that we did that is we went to the -1 Fresnel zone and found where that was. Then we moved over until we found the +1 Fresnel zone. And by averaging those distances, that gave us an approximation of best focus. By using an aperture here, we could effectively change the diameter of the lens that we were testing, and we found that doing that changed the delta Z of our Fresnel zones.
For the last part of the lab, we wanted to create a diffraction limited system, and we did this by isolating the area disk pattern from the incident beam. What was recommended for us was to have at least a area disk pattern radius of 200 microns, and we wanted to play it safe, and so we made that area disk radius 250 microns. And we can use this particular equation to solve for the F number of the system, which we get to be 161.914. And knowing that the focal length of the test lens that we're using is 1 meter, we can find the diameter of the aperture necessary to achieve this area disk pattern radius to be 6.18 millimeters. We can then also find the cutoff frequency, knowing lambda and the F number, and we found this to be 9.76 line pairs per millimeter. And using this number, we can calculate the necessary slit width to achieve this entire system, which we found to be 0.102 millimeters.
We placed the lens over here, a test lens. We adjusted the aperture behind it to make a diffraction limited system. We found the best position for the microscope using the black dot method and put it there. We made sure that the microscope is focusing onto a slit. We made sure that the size of the slit is around 0.1 to allow only the area disk to pass through it.
So given our appropriately sized slit, we wanted to measure just the area disk of the incident beam, and we did this by having that appropriate slit act like a rect function and scan across the input beam's incident beam. Our output was a Gaussian-shaped LSF at this spot of best focus, and what we did is we performed a discrete Fourier transform on the LSF to get the MTF.
This plot shows the MTF of our system shown in green, and then the theoretical is shown in red. And we can see that our curve is slightly degraded from the theoretical one, and that's probably due to aberrations in the system, with a cutoff frequency of about 9.7 as expected.